How's everybody doing today?
So good.
So beautiful. Seems like we should be outside.
How are you?
Good. Scrambling through the week. I apologize that I didn't post the lecture until like 10 minutes ago, but it's there now. So if you have not downloaded it yet, go ahead and do that.
Are you involved with tomorrow's and Saturday's datathon at all?
Somewhat. I'm not like, the main driving force behind that, but I've been helping a little bit with some of the organization, and I'm going to volunteer Saturday morning for, part of the day as like, whatever, being available if people have questions. I don't know how much help I'm going to be, but yeah, it seems like a cool event.
How many people have signed up?
Yeah, that's a good question. I don't know. I was at the preparatory workshop yesterday, and that was not like a huge crowd, but there were a handful of people there. So yeah, but it seems like a really cool event. I thought you guys might be interested because you're like, you would be perfect for it. Okay. Yeah, so why don't we go ahead and get started? Welcome everybody to today's class. So Professor Phillips probably mentioned this on Tuesday, but I'm going to reiterate it, that on Tuesday, March 29th, we're doing peer feedback class day, and we are requiring in-person attendance on that day, okay? If you have some, really compelling reason you can't do that, please get in touch with us and we'll try to figure something out. But if you can, if there's any way possible, please be here in person because we are expecting in-person attendance that day so that we can do the peer feedback sessions. We will not be running the whole class in Zoom, so we won't be like putting people into breakout rooms in Zoom. Okay, let's see, anything else? Yeah, remember that the homework 7 is due tomorrow. Hopefully that's coming along okay. And today we're going to be talking about clustering. Any questions on course logistics or anything before we get started? Okay, and also a reminder that Datathon for Justice is happening this weekend. We were just discussing that, but do see the announcement that I posted for the link if you're interested in that. It's a great event, should be a lot of fun. Okay, so today we are talking about clustering. I really like this topic, so I'm excited for today's discussion. So what is clustering? Clustering is an unsupervised learning technique, and we're going to cover the following topics in today's lecture. The difference between supervised and unsupervised learning, clustering, and we're specifically going to focus on the most famous clustering algorithm that there is, which is k-means clustering. And then we'll have another lecture where we talk about some other methods. Okay, so here are some readings that I encourage you to check out. Okay, so first of all, before we dive into clustering, it's good to understand the general difference between supervised and unsupervised learning. What we have been doing so far has been supervised learning. And in supervised learning, you have basically inputs X, and then you have some label function Y associated with those inputs. So you have some function that maps an input X to an output or label Y. And you're trying to learn that function. Okay, so this can take a couple of different forms. So in the regression context, Y is some real valued number, and we're trying to, approximate this with a linear function or maybe some other generalization. And then in classification, this Y is a categorical variable corresponding to a class. Okay, so the tools there are a little bit different. We talked about the KNN classifier. We talked about support vector machines. We talked about decision trees. All of those were classification methods for supervised learning when y is a categorical variable. Okay, so one difficulty of supervised learning is that labels can be expensive or even impossible to obtain. So in unsupervised learning, we don't have any kind of label function, okay? So the y is just gone, and we're sort of just trying to discover like the, just the intrinsic structure of the data itself. But this is unlabeled data. So unsupervised methods are often used to identify a previously unknown structure of the data set. So we might want to discover what the structure is. Okay, and so some examples of unsupervised learning are clustering, which we'll talk about today, dimension reduction, which we'll talk about in the future, density estimation, anomaly detection, etc. And they can also be a useful precursor to visualizing data because many visualization approaches will first cluster the data or will first apply dimension reduction to the data and then you'll see a visualization of that. Okay, so today we're talking about clustering. So what is clustering? So clustering is basically the task of trying to find meaningful subgroups in your data, which are not a priori known, so discovering unknown subgroups in the data, and we call those clusters. So the goal is that you want to take your data set, you want to partition it into different groups so that points in the same group are similar to each other and points in different groups are dissimilar to each other. Okay, so some examples where this might be a useful thing to do in social network analysis. Clustering can be used to find communities, groups of people who know each other or who hang out together. In ecology, you might want to cluster organisms that share attributes into their respective species. And then we looked at in this data set, you were exploring that in your homework, right? Doing classification for the digits. You could also think about, though, just doing clustering on the digits, just grouping the similar images together without necessarily knowing what the labels are. So when the digits are unknown, you might want to do that. Okay. Okay, so just to kind of make sure everybody is awake, what is the difference between clustering and classification? Yes. Right. Yeah, right. And specifically in clustering, there's no labels, right? You're trying to group the similar things together, but you don't know what that group corresponds to. And in classification, you have explicit labels. This is this cell type, or this is this type of thing. Okay, so a couple of challenges that we face when clustering. Well, one of the big ones is we have to make sense of what it means for two items to be similar. So that's really tricky. What does it mean for two items to be similar? There's lots of different ways that you could measure distance or similarity between data points. So for example, Euclidean distance, that's just the most basic thing that you could do. What's the distance between 2 points in space? You could also look at Pearson correlation, Manhattan distance, weighted distances, Shikard coefficient. I believe we'll expand on some of those in future lectures, but not so much today. We'll just mainly think about clustering with Euclidean distance, but we'll see some examples where it doesn't work out so well. Okay, and then another thing that's challenging about clustering is is that in general, there's no ground truth to compare it to. So this can be a little bit unsatisfying. In classification, we have our labels. So we have our training data and our testing data, and we have, very good ways of evaluating performance. We're looking at how well does it perform on the test data set. But without labels, how do you know when you've gotten a good answer? That can be a trickier thing to evaluate. Okay, so we can't use cross-validation. Sometimes we may use visualization or human inspection, and sometimes we come up with certain heuristics that we calculate to try to quantify, is this a good clustering? Okay, so clustering methods come in a number of different flavors or families. First of all, you have your partitional algorithms. So what those do is take the data and divide it up into a certain number of bends. Maybe you've decided you want to partition it into 10 bends, and it'll, cluster it into 10 clusters. So the bins, it might be set manually, like you may have said, use 10 clusters, find the best 10 clusters, or some algorithms can automatically detect a good number of clusters to use. Another approach, which is useful if you have no idea how many clusters might be present in your data set, so you don't know what to tell it to do, are hierarchical algorithms. And how these work is basically by building a tree on the data by iterative splitting. So it's kind of like decision trees, right? So first you figure out, well, what's the best way for me to cut my data set in half? And then if I was gonna, peel off another piece, what's the best way to do that? So you come up with all of these like branches in your data. And this tree is called the dendrogram. And so basically, if you're really high up the tree, if you look at the clusters you get at that point, you might get like 2 or 3 or some small number. If you go really far down the tree, it's clustered it into a bunch of tiny little things. You're going to get a large number of clusters. So you're going to get this whole like hierarchical clustering structure. So that can also be useful. We'll talk about that a little bit more in the next lecture. Okay, there's also by clustering. What does this refer to? So generally today we're going to be thinking about, we have a collection of data points, and associated with each data point is some vector of features, and we want to cluster the data points into similar groups. In some applications, you might also want to cluster the features themselves into similar groups. So think about, you might have a large data set of patients, and you might have all of their genetic information as the features. You might want to both simultaneously cluster the patients into similar groups and also cluster the genes into similar groups. That gets a little more complicated. And then there's also fuzzy clustering, where most of what we're going to talk about are sort of hard cluster assignment rules. You're either in cluster 1 or 2 or 3, but it can sometimes be very useful to give yourself like a little margin of error and to say, well, I don't know exactly where this point belongs. I'm going to say there's a 70% chance it's in cluster 1, 20% chance it's in cluster 2, and a 10% chance it's in cluster 3. So in fuzzy clustering, you don't get an actual label, you get a probability distribution of what's your probability of being in each cluster. Okay, right, so there's many variants of all this implemented in scikit-learn, which is what we'll be looking at. And we will focus in this class specifically on k-means, that's what we're going to talk about today, and then hierarchical clustering and dbSCAN. Okay, so now let's get into the details. Actually, any questions before we get into the details of k-means? Okay. Okay, so k-means. So we start off with a collection of points, x1 through xn. And let's say these are living in a d-dimensional space. And what we do is we try to find k centers. Let's call these centers mu L, where L ranges from 1 to k. And we want to assign each point x to cluster CL with center mu L in such a way that the following function is minimized. What do we want to minimize? We want to minimize over all different possible clusterings C, the sum over the clusters, the sum over the points inside the cluster of data point minus the center squared, or the distance of the data point to the center of the cluster squared, okay? Right, so we're summing over the clusters, summing over the data points, and then we're looking at the distance between the squared distance of a data point to the center of its cluster. Okay, so mu L is just the mean of points in CL, right? So we have clusters C1, C2 through CK. So this is the total intra-cluster distance. Sorry, the total intra-cluster distance is the total squared Euclidean distance. Yeah, I already said that. Okay, so basically it's a measure of the internal coherence of the clusters. This is going to be small when you have data points that are not too far spread out around the mean of the cluster. It's kind of like variance, but it's only looking at the variance inside the cluster. Okay, so how do we actually minimize this thing? The most famous algorithm and pretty simple to implement is called Lloyd's algorithm. And how does this work? So to try to minimize this thing, we can apply Lloyd's algorithm, which proceeds as follows. So we input a set of points, x1 through xn, and an integer k. We have to tell this algorithm how many clusters we want to compute. And then we will pick k starting points as centers, mu1 through mu k. This can be done in a number of different ways, so not one single right way to do this. You might just pick these points randomly. Think about probably just picking these points randomly for now, and we'll talk more about that in a minute. Okay, and then what you do is, until the algorithm converges, you assign each point to the cluster CL with closest center mu L. Okay, so what does that mean? It means that for every data point, you have your k different centers, mu1 through mu k. So for every data point, you compute what's my distance to mu1, to mu2, to mu k, and then you see what's the smallest one, and then you assign that point to that center to the associated cluster. So then we assign the point xi to the cluster CL with the smallest distance to mu L. Okay, and so once we do that, we then update the centers by, all right, so we've changed some assignments. Now we're going to recompute the mean after we change the assignments. We get new mu Ls, and then we just keep repeating this, right? So we sort of check all the distances to the centers, shift points, then we update the mean, and then we check all the distances to the centers, and we will, move points around if needed, and then update the means. And we just keep repeating this until we converge, until nothing is changing anymore. Okay, so here's like a little illustration. So let's say we have this data set of gray points, and let's say we initially we're going to cluster it into 3 clusters, and we randomly pick these 3 colored points as the initial centroids. Then what the algorithm is going to do, right, it's going to go through every point in the data set, ooh, this one is closest to the red centroid, so I'm going to say I'm red. This point is closest to the green centroid, so I'm going to say I'm green, etc. These are closest to the blue. So those centroids have now defined a partition of the data in a very natural way, just based on the nearest distance. But now that we have this partition, what do? Now we calculate the mean of the red points, of the green points, of the blue points. And notice now that mean is going to shift a little bit, right? So what used to be the centroid is now going to change because now we are computing this mean. Okay, so like, for example, here, now we're going to compute the mean of the green points, and that's going to shift this thing down a little bit and to the right a little bit. Okay, so now that we have shifted the centroids, we're going to do that whole thing again. Now we're going to look, now this is our new centroid, and so these are the points associated with it, new centroid, these are the points associated with it, etc. And we're just going to keep iterating this until convergence. It looks to me like this has not converged yet, that if you kept repeating this procedure, I'm guessing what you would probably end up with is, these points being together, these points being together, and those points being together, but it would take you a few iterations to get there. Okay. All right, so some things to think about when you're doing this algorithm. How do you pick K? How do you know how many clusters to use? Well, if your data is, two-dimensional or low-dimensional, you can try to plot it. You could try to come up with, kind of take a look at the data and see how many clusters you think you see. That will only work if your data is low-dimensional, though. You can compare the value of the total intra-cluster distance for different values of K. So for example, this is the thing that we're trying to minimize. So we could look at, if I have different values of K and I have different clusterings corresponding to those different values, what is the intra-cluster distance here? Now, can anyone think of a problem of just, picking the K that corresponds to the very lowest value of this thing? Yeah. Exactly, right. So this thing will always decrease in K, right? So you're not looking to minimize it in the classic sense, but you're kind of looking for, when does it level off, kind of like the elbow. We'll talk about that later. Okay, so, but anyway, by sort of looking at how the intercluster distance decays in K, that can be helpful. And you can, try out a bunch of different values, and we'll see, we'll talk about in class one heuristic that you can use for selecting between a lot of different values. Okay, so another thing that's unclear is initialization. So how do we pick the K starting points? And the algorithm will can give pretty different results depending on how it's initialized, what the initial centers are. So some approaches are, well, just pick them randomly, right? Just randomly pick points in the domain. Another idea is, well, maybe try to make sure they're spread out enough, though. Don't just totally pick them randomly. Make sure you don't get points that are too close together as your centroids. You can also just do it manually. I don't think many people really do it manually, but one could. Okay, and then finally, another kind of thing you have to think about is convergence. What does it mean for this algorithm to converge? I mean, really what it means for this algorithm to converge is that, as you're doing this iterative procedure that I've outlined here, that when you get to this step, no point changes cluster assignment. So if you get to the point in the algorithm where once you compute your centroids and compute the assignments, nothing changes, then you've converged, right? Then nothing is going to change. So if you get to that point, you've converged. You may wonder, well, what if that doesn't happen? Or what if it takes a really long time? Well, you can always say, you can always limit the number of iterations, say don't do more than 100 iterations of this algorithm, and let's just take what we get after 100 iterations. Or you could have some kind of criteria that the centroids aren't moving very much. Maybe they're moving a tiny bit, but they're not moving very much in each iteration. Okay, so there's actually a little visualization of k-means, which is kind of fun to play around with. So you might want to check this out. You can choose how to pick the initial centroids, let me say randomly, and then you can choose what type of data set you want. Let's pick an easy one, which is a Gaussian mixture. Okay, so then if we have a Gaussian mixture, I'm going to randomly throw up some centroids. Ooh, see, we got two in the same. Oh my gosh, that seems really unlucky. So this is a good illustration that random centroid placement is not always a good idea, right? Put all three of our centroids in the same cluster, and that can happen. Okay, so let's see. So this is just gonna update the centroids and then update. You can kind of watch this progress. So for this one, I feel like it will get the right answer eventually, but we got really unlucky in getting all of those points. Actually, I wonder if it ever is. Yeah, so actually this is a good illustration of what can happen. This doesn't usually happen, I would say, but it can happen. And here we kind of got unlucky. All our centroids got close together and it found sort of a local minimum of this objective and it stopped. But we can see if we try this again, let's try it again. Let's do the Gaussian mixture, centroid, centroid, centroid. Let's see how it proceeds. Yeah, this one's also not going so well. Okay, so let's so one thing that can be really effective is to do something called farthest point initialization. That's where you make sure that the centroids that you start with are kind of far apart. So if we do this on the Gaussian mixture and we start off, we use farthest point initialization. Now we've made sure our points are pretty spread out. And you'll notice if we do that, boom, we've converged like already. You converge like almost immediately. So that's cool. So on this kind of data sets, as long as you do a good job with your initialization and et cetera, things tend to go well, but it can be difficult. So let's do another, okay. Let's take a look at this example. Smiley face. So how many clusters would you say there are here? 4. We can kind of do some, even if we initialize one in each cluster, for example, let's see what happens. So this algorithm, it looks like it's finally kind of converged. It is going to break apart that big outer circle. Like there's no way in which it ever keeps all of those points together because they're so far apart, right? So because the point over here is really far from this point. So this is an example of a data set where k-means would not work very well, and it's just never going to work on this type of data set. Okay. All right, so you can play around with that. It's kind of fun. You can see the effect of the initialization, et cetera. All right, some properties of k-means. The computational complexity is order n, number of data points, times k, number of clusters, times d, number of features, or the dimension of each data point, times I, which is the number of iterations that it takes until you converge. So this is generally considered to be a very fast algorithm, right? So it's linear in the number of data points. The only thing that you don't really know exactly is how many iterations it's going to take to converge. So that I is a little bit unknown. But if there is a good cluster structure to your data, I tends to be pretty small, actually. Okay, so this is a fast algorithm. One thing that's important to keep in mind, and that is that Lloyd's algorithm will find a local optimum, not necessarily the global optimum. Okay, we want to minimize this thing, this function. We want to find the C that makes that as absolutely small as possible. But the algorithm that I told you about is not necessarily going to converge to the very best clustering in terms of the global minimum of this thing. It's just going to converge to a local minimum. Okay, and we'll talk a little bit about what you can do to try to work with that. It is two other things to note is that total intra-cluster distance does decrease at every iteration of Lloyd's algorithm. So it's always going down and never goes back up. So that's a good property for convergence. And the total intra-cluster distance decreases with larger k, as we already talked about, right? So it's always going to get smaller if you increase the k. Okay. All right, is that making sense? Yeah, good. Yeah.
Sorry, so you were saying that Lloyd's algorithm always finds a global minimum because it keeps decreasing, or you were saying?
No, it keeps decreasing, yeah, but there's no guarantee it's going to decrease to the global minimum. It will just keep decreasing until it gets to a local minimum, but then it's going to stop at that local minimum. You know, so think about a function that might go like this and then down here. So it would decrease until it got there, but it would never find this lower point. Yeah. Other questions? So what people do in practice, which we'll talk about a little bit later, though, is they'll just do a bunch of different initializations. You know, they'll initialize it in a lot of different ways. And so then you'll see, okay, here it converges to this, here it converges to this. And then I can see, well, what was the best one that I got? So also that's not guaranteed to give you the global minimum, but it's guaranteed to give you a decent, well, you know, pretty good, usually, local minimum. Okay, so let's see how we do this in scikit-learn. They have a nice implementation of k-means. So here's our imports. And let's take a look at a first example, which is an easy example, kind of the easiest clustering problem. And it's just a bunch of Gaussian blobs. So we can make this data with the make blobs function from the sklearn data sets. And this is what we get, right? Okay, 3 Gaussians. So let's look at running k-means. There's a couple of different parameters that you can input into this function. This one is mandatory, number of clusters. You always have to tell it how many clusters. For this example, we'll ask for 3 clusters. The other ones are optional in that they have defaults for these. So if you leave these out, it's okay, but you should understand what they are. In init is how many different initializations you use. So like I said, because it's only converging to a local minimum, in general, it's good to do a lot of different initializations and then pick the best one that you get. The default for this is 10, but you can increase that if you want. And then init specifies how you do the initialization. Do you do it randomly or do you do it with some other heuristic? And then max iter specifies how many iterations of the algorithm you're going to allow. And the default for that is 300. So if you leave that out, it'll default to 300. Okay, so let's see if we run k-means. And let's say we just do one initialization and we do one iteration and we choose our initial centroids randomly. We are not expecting this to work very well, right? This is not a good example, but we can get lucky, right? Here we got lucky. But if we keep doing this, normally we don't. Normally that's not sufficient to get a good clustering, even on that easy data set. I'm getting a lot of good ones though. I feel like, yeah. Okay. So as we see, this is not a smart way to do k-means. Essentially, we're just doing random initialization and then assigning points to their closest center. So let's see how we can make this better. So one thing that we should definitely do is not just do one iteration. We're not going to converge in one iteration. So here, if we increase the number of iterations to 5, you can see overall things go better. See, most of the ones I'm getting, we get a really good clustering. Still, it's not always guaranteed. If I keep doing this enough times, ooh, yeah, we got a little unlucky there, but we got, a lot better results when we increase the number of iterations. Okay, so now let's think about these other arguments here. So first of all, the init, or the number of initializations that you do, so that's the number of times the k-means algorithm will run with different centroids. The default is 10, so increasing that is definitely going to help, or just leave it to the default. And then for the initialization, probably the two most common ones are random, picking the k random points, picking the k initial centroids randomly, or using a procedure called k-means plus plus. That's actually the default. And what that does is basically ensure that the centroids, the initial centroids, are not too close together. It's actually still random, but it'll like randomly pick a point in the data set as the first centroid. Then it'll sample the next centroid in a way where the chances that you get picked are proportional to the squared distance from that point. So it's still random, but it's very unlikely that a point really close to you gets picked because of how the random sampling is done. So this k-means plus plus will, with high probability, pick points that are well separated. And that's quite useful. And so that's the default. So we can see if we do that here, notice we're not specifying either of those parameters. So they're using the default, which is 10 different initializations and the k-means plus plus initialization. Even in one iteration, which we saw before was not sufficient, but with the proper initialization and number of iterations, sorry, not number of iterations, number of initializations, we're still getting really good results even with one iteration. I know there's a lot of different things going on here, but hopefully all these different pieces are starting to kind of click. Okay. Okay, any questions on those parameters that you input? Okay. Okay, so let's look at a few more at some more complicated data sets. So minimizing the total intercluster distance is a good idea when your clusters are convex and when they are isotropic, like you have typically the same amount of spread in each direction. But a lot of times that's not the case. So let's look at a few other types of data and see how the algorithm does when we have clusters which vary in density and size, clusters which are anisotropic. So think of kind of more of an ellipse than a circle, you know, it's like elongated, and also when they are non-convex. Okay, so here's a first more interesting data example. So we're actually using the make blobs function again to create this data set. But these are sampled as like Gaussians with the same variance, but then in this picture, we're only looking at, I think it's about like 10 points from this Gaussian and like 100 points from this Gaussian, and I don't know, maybe 160, 170 points from this Gaussian. So these Gaussians have the same standard deviation or the same spread, but we don't have many points from this one. So this one's quite small in terms of the number of points, which means like its density is low. Okay, so, but we see that doesn't really seem to be a problem. We can repeat this a few times. And even though this cluster has not very many points at all, because the sizes of these clusters are about the same in terms of like, you know, how their diameter, if you will, it does fine. Okay, so let's make it a little harder. Let's look at the following example. So here, what do we have? We have two clusters that are pretty compact, that are very dense. And then we have another cluster. This was actually created by like two sort of overlapping Gaussians, one that was more dense and the other that was less so. But as we can see, they overlap. So it makes sense to think of, you know, all of these points up here as one large cluster. And what we see happening here when we try to run k-means on the data, you know, these points here on the edge, it thinks they should go with the blue cluster, and some of these points over here, it thinks they should go with the yellow cluster. So it's having trouble, and the reason it's having trouble is because this big cluster is so much more spread out than those little ones, right? That diameter is so much bigger than these that they're not kind of on the same scale. One way you could think of, here, I can do this a few more times so we can see that it's kind of the same story. You know, one generalization you might could do would be, well, you know, maybe it's because the notion of distance that it's using is not right. You know, somehow we want to adjust our notion of distance when we're in this cluster where points tend to be really spread out. Maybe we should kind of like, I don't know, scale the distances with nearest neighbor distances or something along those lines. But the traditional k-means is going to have trouble. Okay, and then one final example here where k-means does not, actually not the final example. I think we have two more examples. Another example illustrating where it has trouble is on anisotropic point clouds. So here, actually, we've just started off with this data set, and then we've applied a linear transformation that stretches it in this direction. So if you take this data and you stretch it in that direction, you get this data right here. And you can see that now, if you apply k-means on this elongated data, it's breaking apart this large cluster, and it's putting these two things together, even though they're pretty well separated. So again, it's not really doing what we want. You know, we would want all of this to be a cluster together. Okay. And then another example where it doesn't tend to work real well is for non-convex point clouds. So here I was calling this anisotropic. That basically just means like elongated, but they're still convex, right? They're still Gaussians. In this example, they're not convex anymore. Right? This is not a convex shape. It's curving around. So in this example of the moons, if we apply k-means, it has no way of separating, of detecting the two moons, clustering the two moons, I should say, even though they're pretty well separated clusters. But, you know, it puts all these points together because they're sort of, I don't know, closest in terms of Euclidean distance, and these together also. Okay. So let me see, I think that's probably a good place for our 5-minute break. And then when we come back, we'll talk about how we can choose the K. Okay, so what time is it? Let's see. It's 4:26. Let's come back at 4:31. But I'll just be here if you have any questions or anything.
My question anyway, so. So I got to the point where I like found the indexes that like have the misclassified digits here to the peak. So where like the test and the prediction for like 4s and 7s. It gives me
Yeah, so let's see what you're getting.
it's like these.
Oh, good.
values.
Mhm.
Okay, and so then I was like trying to follow like the plotting from up here,
Uh-huh.
and so like in place of the digits and images, I put like the X test with like the mistake
Mhm.
index. Would that be how we're supposed to do it?
Yes, but it's going to be the row corresponding to mistake, but then you need to take all of the columns and you need to you are reshaping. Okay, so I think here you need to say mistake, comma, colon. Do you see what I'm saying?
Oh, so that I get like
I think,
everything.
yes. I
Okay.
mean, I maybe it defaults, maybe it understands, but I'm guessing, yeah. I know they look kind of weird, but that's okay.
Okay, because I can see that they kind of look like 4s, like
Yeah.
a little bit.
Keep in mind, these are the ones that messed up. So these are the
Yes.
hard ones.
Okay.
You can kind of see the 4 in there, but you'll see like, I don't know, maybe something spilled on the page or somehow it got these like high intensity pixels. And I think that's what's messing up the classification.
Okay, so then these, like, I was worried that these were wrong, but these should be okay. Like they should be weird because they were misclassified. Okay.
Was it giving you the same thing without the colon? Did that make any difference?
Yeah, it was.
It was, okay, so that didn't matter. Okay. I go back and forth between MATLAB and Python and I have to like, remember. Okay, well, it's 4:31, so why don't we come back together and get started? Okay, so let's talk a little bit about how we choose the K when we're running K-means. The results of K-means are, as you might expect, very sensitive to how you pick that parameter K. So let's look at the following example where we have 3 Gaussians. If we run K-means with 2 clusters, it'll give us something like this. I mean, which is a reasonable assignment if you're forced to do 2 clusters, but it's not a good clustering, right? All of these red points are in the same cluster, but it's not a cohesive cluster. So when we underestimate the K, we can get clusters that are very non-cohesive. On the other hand, overestimation is also problematic, right? If we think about having these 5 Gaussians here and we run K-means with a K of 7, it's forced to break up some of these clusters. There's really nothing else that it can do. And so now our clusters, well, they're all cohesive, but they're not well separated. So now the problem becomes that some of our clusters are not well separated from each other. Okay, so how to choose K? Well, if we're lucky enough to be in 2 dimensions, we can plot the data and decide. So that's great if you're in low dimensions. It's just normally you're not. You can't do some like dimension reduction and then take a look and then decide. That could be one approach. Another idea related to that function that we're trying to minimize is looking for at which K the total intra-cluster distance tapers off. And then a third thing you could do is a silhouette analysis, which we'll talk about also. But first, let's think about how keeping track of how this quantity, this intra-cluster distance changes in K can be helpful. So let's take a range of K. So we'll vary K from 1 to 10. For each value of K, we'll compute K-means clustering on those 5 Gaussians that we defined previously. And let's take a look at what we get, right? So here are ranging K from 1 to 10, visualizing what the different clusterings we get are, right? So we can see when K is 5, this seems to really be what we want. Clusters are both cohesive and well separated. So let's take a look at what's happening to the intra-cluster distance, okay? Starts off really high here at 1 cluster, then it decays for 2, 3, 4, 5, 6. So this value, K of 5, was sort of what we expected to be the best value. Now notice it's not the smallest possible value, right? These values over here are smaller, but how would you kind of describe that point in the graph? What's that? Yeah, it's like the elbow of the graph. I mean, I kind of find that the best description, right? So you're looking for the elbow in the plot. You're looking for, not the smallest value, but when it really levels off. So in some ways, this is kind of like linear regression. We know if we throw in more predictors, the R-squared value is going to go down, but how much is it going to go down? We want to like find that sweet spot where we're having it go down substantially. And if not, then let's not worry about it. Okay. So, right, so we can do this plot and we can try to, again, this is something we can visualize and we can try to determine what that elbow is. That's generally a good value for K. Okay. Oh, and a little note, the scikit-learn implementation returns negative values, opposites of the K-means objective, as scores here. So just keep that in mind when you're actually running this. So that's why in the code, when we're making that plot, we're looking at the negative of the score. Okay. Okay, so that's one thing you can do. Another thing you can do is something called silhouette analysis. So what is this? In silhouette analysis, for each point in the data set, we compare the distance between points in the same cluster and points in neighboring clusters using something called the silhouette score. So the silhouette score is basically a measure of how similar an item is to its own cluster and also how different it is from other clusters. So this is nice because this notion incorporates both a notion of like cohesiveness, of being similar to the other points in your cluster, but also of clusters being well separated because it's also based on how different you are from the other clusters. So this really has both of those things coming into play. And this is how you compute it. So for each data element, I, and cluster L, let's let DIL be the mean distance of point I to all of the points in cluster L. Okay, so we can kind of interpret this. This is a mean, but we can interpret it as basically the distance of point I to cluster L. And so if DIL is small, then I is very similar to items in cluster L and thus to cluster L. And if it's very large, then I is very different from cluster L. Okay, so we actually, using this notion, we define the following two quantities. First, we define for each point the mean inner cluster distance, AI. What is AI? AI is the distance of point I to its own cluster, right? To the cluster that contains I. Okay, so if that's small, it means that the point is kind of right in the middle of the cluster. It's similar to the other points in the cluster. And then for each data point, we define the following thing, which we call BI. This is the mean nearest cluster distance. So what is this? For BI, we're going to look at we're going to exclude the cluster that I is in, but if we look at the next closest cluster, we're going to look at the minimum distance of I to a cluster that it's not in, right? So that's basically what it's doing. Here, this is the distance to the cluster that it's in. Here, this is the distance to the next closest cluster, not the cluster that it's in, but the next closest one. Yeah.
Do you mean like the cluster center, or is there like the closest point in that cluster?
Oh, well, keep in mind, these are actually means. So when I say the distance to the cluster, I mean that we're actually computing the mean, like we're computing the distance of the point to all of the other points in that cluster, but then we're averaging that to get a notion of distance to cluster. And that's similar to like the distance to the centroid, but slightly different. Okay, great. So once we have these two measurements, how similar are you to your own cluster and how different are you from your next closest cluster, you can combine these together into a silhouette coefficient. And so the silhouette coefficient for data point I will be BI minus AI divided by the maximum of AI and BI. So because of this normalization by the maximum, it's always going to be a value in between -1 and 1. 1 will be good and -1 will be very bad, right? So you want values of this thing that are close to 1. Okay, so what would cause a negative value? Why is a negative value bad?
That should have been-
Yeah, I mean, it should have been in cluster B then, right? Like, if it's a negative value, it's meaning it's like distance to a cluster that it's not in is smaller than the distance to a cluster that it is in. That's generally not a good sign, you know, that maybe it should have been in a different cluster. Now, it can depend on the algorithm, right? Different algorithms have different methods of deciding where points go, but in many cases, if this is negative, that's going to be a bad thing. Okay, so then what we do is once we have this score for all of the points, we can take the mean. Now each point has a silhouette score. We can take the mean of all of those scores, and this will give us a single summary number, summary statistic that kind of quantifies like, okay, how appropriate was this clustering? How appropriate was this K? Okay, so let's take a look. So now let's think about having the various values of K, 2, 3, 4, 5, 6, and this is kind of a lot of code. Don't really worry about this. It's just going to plot things and run k-means. Let's take a look at what it's doing down here. Okay, so what is that code doing? Well, this is the data. Again, we're looking at this data set of 5 Gaussians. And if we run k-means with a k of 2, this is the clustering it'll output, these two together, these 3 over here together. And what you're seeing plotted here are the silhouette scores. So these are all of the silhouette scores for all of the green points. It looks like they range from about 0.4, which is not very good, to about, I don't know, 0.7, which is pretty good. And then here are all of the silhouette scores for the black points. These look to be a bit worse than the green ones. Okay, they're lower. Now, if we take the average, just the average score, all the green points, all the black points, the average is 0.53, okay? Which is not very good, right? We would like that to be close to 1. So let's see what happens if we increase K to 3. So now we've increased K to 3 and things get a little better, right? Visually, it's better. And now when we look at the silhouette scores, the ones for the green cluster are good, right? Those are really high. The ones for the blue and the black cluster are still kind of low, but the mean has increased up to 0.627. So that was helpful. It was better than a K of 2. We can keep doing this, right? Increase it to a K of 4. Now, really, all of them look pretty good except for the blue one, which doesn't have it's not very cohesive, right? We've got this kind of split. So you notice that in the silhouette plots that yellow looks good, green looks good, black looks good. The values are still low here for the blue, but again, we've increased the mean silhouette score to 0.65. So again, that was helpful. If we do one more, increase to an N of 5, now we really get what we want. And you notice in the silhouette plots, all of the silhouette scores are pretty high, and the mean has increased to 0.745. Okay, so that's good. Now notice what happens if you now start to make the K too big, right? So we found a good value. Now what happens if we make the K too big? If we make the K too big, now it's going to have to split one of the clusters. So it splits this one right here. And so what do we see? We see the silhouette scores are pretty good except for the red and the blue cluster where they have become quite small, bringing the mean down to 0.66. Okay, so what's kind of nice about this compared with the, find the elbow method is that it's here, we're just looking for the maximum number. And that's a little bit more clear cut because you can have different opinions about where the elbow is. I mean, in some sense, it's nice to have like, okay, let's find the K that corresponds to the largest value of this metric. And you can notice that like the silhouette scores, they can be low because you've, like overclustered the data because you've made K too big and you've split a cluster into two parts. But they can also be low if you have this situation where your cluster is not cohesive. So both of those things make them low, which makes this a good mechanism for selecting K. Yeah. Oh, that is a good question. Let me it will take longer, but I'm trying to think about what the complexity would be for computing these silhouette scores. Yeah, that's actually a really good question, and I'm not sure. I mean, for each data point, you've got to do all of the distances to your cluster and to the next closest cluster. Well, yeah, let me think about that and see if I can find something on the complexity, because I'm not quite sure. Clearly, it's going to take longer than the elbow. And we're doing a very small data set where it's not a problem. But if you're going to run this on like 10,000 data points, it might become slow. Yes, I am confident it will be slower than the elbow method, but I don't know by how much. Okay, any other questions? Okay, let's do one more example, an actual data set, the iris data set that we've looked at before. So here I'm just loading the iris data and I'm plotting the first two features. Remember, in this data set, we have 3 different species of iris, and we have 4 different features that we've recorded, the sepal width and length and the petal width and length. And this is plotting the first 2 features where we see a lot of overlap between the blue and the yellow species. I forget what they're called. You may remember when we looked at all 4 features that we saw some better separation in like features 3 and 4. So in a sense, there's better separation in this data than you're seeing just from looking at the first 2 features. And let's see what happens if we apply k-means on this data and we use all the features that we have available, which are those first 4 features. Okay, so 3 clusters on all of the features. Now here, now I'm plotting the k-means labels, not the ground truth labels. Let me zoom out so we can kind of compare them. The colors came out different. Let me do this again until the colors match. There we go. Okay. So, it's doing good on this red cluster up here. These are getting mixed up as we would expect, but a lot of them are in the right cluster in terms of the ground truth label. So we see it's not doing perfect, but it's doing okay. It's doing pretty decent. Okay, so we see it looks pretty similar to the ground truth labels, but how can we actually quantify how good it's doing? if we do, I said, normally we don't have ground truth labels, but if we did, if we were in the lucky situation where we actually do have ground truth labels available for a data set, how can we compare those ground truth labels with the output of our clustering algorithm, say, given by k-means? Okay, so let's take a look at this. Okay, so, so here are the labels that were predicted, and here are the ground truth labels. So we want a way of kind of comparing them. So there's some different metrics that you can use for this to evaluate the cluster quality if you do have known ground truth labels. And they are the following. So you can look at the homogeneity score. This is the homogeneity metric of a cluster labeling. Sorry, I didn't really mean to say that. So what does this really tell you? A clustering result satisfies homogeneity if all of its clusters contain only data points which are members of a single class, okay? So like maybe your red points have been separated into 2 clusters, but within each cluster, you know, it's like pure, it's all of the same class. Yeah. Oh, like what they, so the ground truth labels are the actual species of iris as recorded by the biologists who actually collected the data and looked at the images, right? So in this instance, we have some ground truth labels available from a domain expert who's said, no, I know that this flower is this species. Does that make sense? Right, so we have that, and now we're comparing it with what k-means predicted, yeah, the labels would be. Good question. Okay, so now we want to sort of assess how much do these match up. Some of the ways that you can do that are by looking at homogeneity, looking at completeness. So a clustering result satisfies completeness if all the data points that are members of a given class are elements of the same cluster. So for this, we can't break apart a cluster, right? All of the red points need to be together in the same cluster, but there could be some blue points or green points. So they're like opposite things that they're really checking for. And then we can put these together with something called a V-measure score, which is the harmonic mean between the two. So this is like homogeneity times completeness divided by homogeneity plus completeness. This should look kind of familiar. Does this sound familiar based on something else we've looked at? Yeah, what does it kind of remind you of? Say this V-measure score. What does this V-measure score remind you of? Anybody? Well, it's related to something that we used, that you can use in cross-validation, but it's like a metric for assessing classification. One thing you can do is the F1 score. Do you remember we talked about precision and recall and combining those two things together in a single score called F1 score in exactly the same way? So you may be wondering, well, what's the difference? Didn't we already do this? But kind of the key difference here is that these metrics are only calculated like up to a permutation of the labels. So what do I mean by that? I mean, if you look at the homogeneity score, let's say we have a clustering that's 0, 0, 1, 1. Let's say those are our ground truth labels. And then our k-means labels are 1, 1, 2, 2. So notice like the labels don't match, you know, these labels don't match these labels, but the important thing matches that the groups are the same, right? That if we grouped the points by those labels, we would get the same partition of the data. Okay, so when you're looking at this homogeneity score, if I run this, right? Even though these labels don't match, it's still going to tell me a homogeneity of 1 because I might as well, I can call the 1s zeros and I can call the 2s 1s and it doesn't care. It's just looking at what the groups are, right? But, okay, for the second one, now the groups aren't the same, right? So now I have in the first clustering, first 2 points are together, but here the first 3 points are together. And so now it's giving me a very bad value of my homogeneity because the groupings are not the same. Okay, so just to kind of compare this with what we did before when we were looking at metrics for classification, like precision, recall, F1 score, there the labelings mattered, like they had to match. So if you looked at the F1 score of 0, 0, 1, 1 and 1, 1, 0, 0, that's going to be 0. It's not going to say, oh, those are the same groupings. It's going to say, you got everything wrong, right? So, so just to kind of highlight these, like the F1 score and those metrics that we talked about for classification, the labels, they have to match, right? 0 has to go to 0, 1 has to go to 1. But in this V measure and these other metrics, they're only up to a permutation of the labels. They're only making sure that the groups are preserved. Okay, so just be aware of that. Okay, so if we look at what those metrics are on the IRIS data set, actually we see they're all around 0.75, 0.76. And you can kind of think of that as roughly, I mean, it's not accuracy, so I shouldn't say it's accuracy, but it's, you know, it's a way of measuring how well the clustering is doing, and it's just kind of okay, but it's not very good. Okay, questions on that? It's fun, right? Yeah, it's fun. What my son used to say when he wasn't sure, he was really unsure about something and he wanted to convince himself that he was going to have fun, he would be like, be fun, with this really unsure sound in his voice. But anyway, so we don't really have time to do the activity in class, but let me point out to you that there is one, and you are welcome to do it and submit it for one of your activities in Canvas. Sorry, do I have it up here? Let me move this so I can see. Let me find it. It's about penguins. Okay, so this is using one of the built-in data sets in Seaborn. And so it's very similar to the IRIS data set, actually, but it's penguins. So you have these 4 different features for the penguins, and you want to classify the species. So it's short. Actually, I don't think it will take you very long, but it's just a good practice for looking at this data, running k-means on it, and then assessing the results by comparing the ground truth labels with the predicted labels using some of those scores. So take a look at that as you have time, and feel free to, yeah, definitely if you still need, remember you need 5 activities for the whole semester. So just make sure that you're getting up to 5 as we're getting closer to the end. Yeah. Yes. Yes, but it's better to to do them along the way. Okay. All right. Thanks, everybody. Have a good evening.